What's up, geeks, and welcome to the channel. In today's video, we are going to take a look at how concurrency is implemented in Java. To do this, we'll start by covering the volatile and synchronized keywords, then check out atomic variables. Now, before discussing each keyword, it is important to understand two concepts: visibility and mutual exclusion, also known as atomicity. Visibility means that changes done by one thread to shared data are visible to other threads or processes. Mutual exclusion means that only one thread or process can execute a block of code at a given time or do updates on shared data via a certain block of codes. So, one ensures that variables are not cached, and the other ensures that operations are done by one thread at a time. Now, let's think, how can concurrency happen? Why would a variable be read differently by two processes? Imagine we have a shared variable, let's say an interest rate, stored in the main memory equal to 3%. The first processor reads it. It doesn't need to change it, just to apply it to a certain value in its program. Then another processor, say the admin processor, wants to increase the interest from 3% to 3.5%. But the thing is, processor 1 has already cached this value in its internal memory to avoid going back and forth to the main memory and provide a faster user experience. Therefore, the value used by processor 1 in its next operations will remain 3% instead of 3.5% until its cache is reset. Unless we define this field variable as volatile. How will volatile solve the issue? Well, the volatile keyword ensures visibility without mutual exclusion, which means that volatile variables are never cached, hence reads are done from the main memory directly. So, the thread must reconcile its working copy of the field with the primary copy every time it accesses the variable. In this example, only the admin processor can change the shared variable. However, we may have more than one thread reading it, so we need visibility. Also, note that volatile can only be used in field declarations. So, methods, classes, local variables, and parameters cannot be declared as volatile. This example also highlights why there are very few usages of this keyword, since a simple instruction such as I++ needs both to read and write, as we first need to retrieve the value of I and then increment it, which requires both visibility and atomicity. Now, imagine that in our previous example, the first processor also had the right to change the interest rate. Although changes are made directly to the main memory due to the volatile keyword, there is still a possibility that both processors perform the right operation simultaneously, which could lead to inconsistencies. That is where Java's synchronized keyword comes in. The synchronized keyword ensures both mutual exclusion and visibility. In Java, the synchronized keyword can be used on methods or to wrap blocks of code. One and only one thread is allowed to enter the wrapped code at the same time, and all variables accessed inside it are to be flushed and updated directly on the main memory. If we are only wrapping read operations on a single field with the synchronized keyword, then we are better off using the volatile keyword as it provides less overhead on the Java application. Now, what if we want to execute read and write operations in a thread-safe environment on one field only without having to deal with the synchronized keyword? Don't worry. Java has provided us with atomic variables, and that is exactly what they allow us to do. Let's first break down this notion by explaining what an atomic operation is. It is derived from the word atom and represents the smallest operation we can do. So, for example, I equals 1 is an atomic operation as it consists of one and only one operation, which is setting the value of I to 1. Let's consider now I equals I plus 1. Is this an atomic operation? It may look simple, but it can actually be broken down into three smaller atomic operations, where first we retrieve the value of I, then we increment this value by 1, and then we set the new value of I to be the value we just incremented. So, atomic operations are not only the smallest operations there are, it is also an operation that is performed entirely or not executed at all, similar to a database transaction. We can't retrieve half of the variable I, either we retrieve it or not. That is exactly where the word atomic comes from in the atomic variables. Operations executed on atomic variables are either executed entirely or aren't at all. Let's take a look at a few examples in code. Let's suppose we have a customer class, and that every time we create a customer, the ID of the customer should be automatically incremented. Now, to implement this, the first step we need to do is create a static ID counter field inside the customer class. A better approach would be to read this value from a certain table in a database or a file, or to not create it at all and use the values of the IDs already stored, if stored, to guess the next increment. But in our case, what we wrote will do fine. Next, in the customer's constructor, every time a new customer is created, we need to increment the value of the counter and set this value to be the ID of the newly created customer. However, notice the concurrency problem with this approach. If more than one customer is being created at the same time by different threads, there is a chance that both of them will be assigned the same identifier. Moreover, setting the variable to volatile will not solve our problem, as every processor in charge of creating customers will need to both read its value and then modify it, in this case increment it by 1. So, to solve this problem, we will need to wrap the incrementing logic inside a synchronized block, or to extract this logic to a separate method and set this method to be synchronized. We just made the creation of our customers thread safe. Now, why are we going through all this? And what do atomic variables have to do with what we just implemented? Well, the same results achieved using the method we wrote can be obtained if we transform our counter to an atomic integer and use the getAndIncrement method provided by its class. You see, this method will ensure that only one thread is incrementing this variable at the same time and that its value is read directly from the main memory. In addition to this, we have the incrementAndGet method. They both do the same thing under the hood. However, in case the ID is 0, the getAndIncrement returns 0 and then increments the counter to 1. Whereas the incrementAndGet will first increment the value, then return the result, which is 1. The most commonly used atomic variable classes in Java are atomic integer, atomic long, atomic boolean, and atomic reference. These classes represent an int, long, boolean, and object reference respectively, which can be atomically updated. Additionally, two main methods exposed by these classes, other than the increment ones we just covered, are the get and set methods. The get method will retrieve the value of the atomic variable from memory so that changes made by other threads are visible and considered. That is equivalent to reading a volatile variable. On the other hand, the set method writes the value to memory directly so that these modifications are visible to all other threads, and that is equivalent to writing a volatile variable. Another heavily used atomic method is the compareAndSet. This method takes two arguments and checks if the value of the atomic variable stored inside the memory is equal to the first value passed to the method. If that is the case, the variable is set to the new value. If not, no changes are applied. And that's it for this video. I hope it was helpful. Thank you guys for watching. Take care, and I will see you in the next one.